The focus of this section is to discuss the liability analysis in a single area. If you remember, in the previous section, we defined a generating capacity reliability evaluation as hierarchical level 1. And there were two levels over there within that level. One is the single area, the other is the multi-area. In the single area, all that we are interested is to consider the adequacy of generation to supply the load. And we assume that the transmission capacities are adequate to carry the generation from generating points to the load points. What is the overall objective of a power system? The overall objective is, of course, to supply the electrical energy to customers. But this has to be done with a service quality that's acceptable and which is economically justifiable. Now, the generation adequacy, the idea of generation adequacy, deals with the ability of the system to supply the load with these attributes. Now, we have to understand that there are certain factors which produce the uncertainty. For example, the load may be higher or lower than what we have forecast for the future. Some generating units might fail. Some generating units may be put on planned maintenance. And in some cases, like hydropower or wind power or solar power, the basic energy may not be adequate to produce enough power. So all these factors need to be considered in planning for the future. Now, there's another term which we use, the security, as contrasted with the adequacy. Now, in the adequacy, we are not dealing with the sudden shocks which can upset the and cause cascading failures or instability and so on. And the security does. Now, the generation adequacy is usually measured through the use of some reliability index, which we can also call as the adequacy index. And this quantifies the level of adequacy or the level of reliability. Now, some utilities, they may rely on the adequacy criteria whose value has been chosen based on some engineering judgment. And these, as you will see, that these kind of criteria are called the deterministic. However, if you use the probabilistic indices, then you will see that you are able to incorporate more factors which contribute to the uncertainty. So the reliability indices can be broadly divided into two categories. The first is the deterministic indices, And these indices, they reflect some kind of postulated conditions. And as you can imagine that they may be good in certain circumstances, but they may have only limited applicability when many of the factors which affect the reliability change. The probabilistic indices, they try to incorporate the uncertainty which is inherent in power system reliability problems, and they have the capacity or the capability of reflecting various parameters which can impact system reliability. So the probabilistic indices, they permit the quantitative evaluation of system alternatives through the direct consideration of parameters which influence reliability. So it's much easier to do the cost-benefit analysis or to do the trade-offs between various expansion plans. The deterministic indices which have been used, one of these is the percentage reserve margin. The percent reserve margin is defined as the installed capacity minus the annual peak load divided by the annual peak load and multiplied by 100. Now, as you can imagine, that this percentage reserve does not directly reflect system parameters such as the unit size, unit outage rates, load shape, and like the availability of the basic energy like in wind power or in the solar power or the hydropower. However, it does provide a reasonable relative estimate of reliability performance if parameters other than the margin remain essentially constant. So sometimes what is done is that people will try to do they will try to establish the percentages based on the probabilistic analysis, and then they can use that percentages for some time, and then again they will come back and try to establish the percentages again through the probabilistic analysis. So the other is the reserve margin in terms of the largest unit. So this recognizes the importance of the unit capacities in the relationship to the reserve margin, because the units which have the larger capacities, when they fail, they are going to have more dramatic effect on the reliability than the smaller units. Now, the probabilistic indices. One of the very commonly used probabilistic index is the loss of load expectation. So the loss of load expectation has been defined in two ways. One is what we call the daily loss of load expectation. So this is the expected number of days per year on which insufficient generating capacity is available to serve the daily peak load. So here the concern is that whether the daily peak load on a given day was satisfied or not. So therefore, the information that you will need for the computations are only the daily peak loads of the year. The hourly loss of load expectation is the expected number of hours per year when insufficient generating capacity is available to serve the load. So this will consider all the hours of the year for the load. So therefore, it's a lot more comprehensive in incorporating the changes in the load shape on their impact on the reliability of the system. So you can see that both of these indices, they do not provide any information on the magnitude of the capacity shortages because they are considering only the loss of load. If the loss of load is 1 megawatt or 1000 megawatt, that is not being reflected in the loss of load expectation. They do not also try to give you the indication of the capacity shortage events duration, that when they occur, what kind of duration, what magnitude of duration they will have. And as a consequence of these, they do not provide you any expected amount of unserved energy information. The other index which has been used is the expected unserved energy. So this index measures the expected amount of energy which will fail to be supplied per year, either due to the generating capacity differences and or the shortages in the basic energy supplies, like in the hydro, in the solar and wind power. Now, neither of these sets of indices, they provide any information about the frequency of the loss of load events. Now, the frequency and duration of capacity shortage events, there is a set of indices which can be used to characterize the frequency and duration. The frequency of generating capacity shortage events is defined to be the expected number of such events per year, and duration is the expected length of the capacity shortage events when they occur. The term expected here is used in the sense of mean value or the average value. Now, the frequency and duration indices, they will use the hourly load information, and thus they reflect the influence of the shape of the daily load cycle. The frequency and duration indices also model the units with more parameters. That they will require the transition rates between the various states, whereas the loss of load expectation and the expected unserved energy indices, they would not require the information on the transition rates, but only on their probabilities. Conceptually, the frequency and duration indices are superior to the loss of load expectation because they provide more information, but they also have greater requirements for data. Now, how do we compute these indices? The basic approach is the following. You first develop the model for the generation system, then you develop the model for the load, and then you combine these two models to create the model for the generation reserve model. And the generation reserve model is the one which will give you all these indices. Now, to develop the generation system model, we will need the models for each generating unit. For the adequacy calculations, the two models which are most frequently used are the two-state generating unit model and the three-state generating unit model. In the two-state model, we have the upstate and we have the downstate. So this is also called the forced outage state, and here the unit is fully available. So this is the failure rate, this is the repair rate. Now, if you want to compute only the loss of load expectation and the expected unserved energy, then you can basically, all that you need to know is the probability of this state, which is called the forced outage rate. The forced outage rate for the generating unit is not a rate, but it's the probability of failure. It's the probability of this state. And this can be computed from the service hours divided by service hours plus forced outage hours. So what's the transition rate? The transition rates can be explained as follows. If you have got the states of a unit and Nij is the number of times the unit changes from state I to state j, then the transition rate from state I to j is given by lambda ij is equal to the number of times you go from I to j divided by hi, where hi is the time spent in state I. So for a two-state unit, lambda is the failure rate. So this will be number of failures divided by the service hours. And mu is the repair rate. So this will be the number of repairs divided by the forced outage hours. So, and the P2 then will be lambda divided by lambda plus mu. For three-state units, you may have a diagram like this. This state represents the unit is fully available. This state is the state of partial capacity, and this state is the state of zero capacity. Now, in a large unit, you may have more than one partial capacity states. But many people feel that you can represent those partial capacity states by an equivalent D-rated state. So this would be a three-state unit. Now, if you have information and you want to have more than three states, you can do that. And the algorithms are now very powerful. They can incorporate units with any number of states so long you have the data available for them. So generation system model. So what you do is combine the models of the units to find the probabilities of the various capacity levels. So in the module 2, we discussed how we can combine the 50 megawatt units to create the probability distribution of the whole generation system model. Now, the generation system model, when developed, will look something like this. These are the various capacity outage levels, and these are the capacities in. You know, it is kind of customary to develop these models in terms of the capacity outage, then capacity in, but you can do it either way. So these probabilities, they are what we call the cumulative probabilities. So for example, this is a probability that the capacity out is greater than or equal to 0. And this is a probability that the capacity outage is greater than or equal to 50. So that's why they are called the cumulative probabilities. To develop a load model, what you do is that you take this load curve where you have got the time, and this is the load. So if you want to find out the probability of load equal to or greater than Li megawatt, then basically you draw a line here and then find out the number of hours the load is greater than that level and divide by total number of hours, and this gives you the probability of the load equal to or greater than this value. Typically, the load model is developed in discrete increments. So the difference between one load level and the next load level is a constant increment. So this is basically you are trying to discretize the load into fixed increments, and the increments can be made as small as you want to develop an accurate load model. Now in practice, there are algorithms to develop these load models, and those algorithms are very efficient. So in the example that we had in module 2, we had these load levels, and these were the probabilities over there. Now these load and the capacity models are combined to create what we call the generation reserve model, or also called the margin table. For example, in this case, if you have the capacities are 150, 100, 50, and 0, and the loads are this one, then the margins over here will be capacity minus load, capacity minus load, and so on. So obviously the negative margins, they represent the situations when there's a loss of load. Here the capacity and the load are exactly equal. Here the capacity is greater than the load, but here is smaller than the load. So if you want to compute the probability of capacity being less than the load or the probability of load loss, then basically you have to compute the probability that the margin is less than or equal to the first negative margin. So you can see over here that the loss of load probability is equal to the probability of the negative margins, and this can be computed by probability the capacity is equal to 100 times the probability load is greater than 150 in this case, because if the capacity is 100, then the load has to be equal to or greater than 150 for there to be a load loss. Because if the load is less than 150, then there is no load loss. So all these conditions can be combined to compute the loss of load probability. To compute the expected unserved energy, you can take each margin and multiply that by the loss of load in that margin multiplied by time and sum it over all the margins. So if you do that in this example, you will get this value. And that's the end of this module.